Hello, operating systems people. This is Gabe Palmer, and today we are going to be talking about deadlock, the most fun of the horrible things that happen to us as we start to execute our systems. So, deadlock is essentially something that I alluded to last class, and effectively the idea that something has gone wrong with synchronization, right? And as if you needed any more motivation to be terrified of synchronization, concurrency, and parallelism, deadlocks are one more thing. Unfortunately, we still tend to need concurrency, parallelism, and all these things to make use of the system's resources at all, so we live with these things. But today we're going to learn about yet another nail in the coffin that unfortunately is never going to get cast into the ground. Deadlock. And the whole idea behind deadlock is simply that there's a set of blocked processes, each of those processes hold some resource. And I'm going to be talking about resources fairly generically today. They may be a critical section, it may be a lock, but it could also be a device, a hardware device that only one client can use, only one process can use. Or it could be memory. It could be mallocked memory. As we call malloc, we're actually asking for a resource or a portion of a resource, right? So, for deadlock to happen, you have to hold a resource. You have to wait to acquire some resource held by another process within a set of these blocked processes. And when those two conditions happen, we'll go over a few other conditions. You can end up in a case that intuitively means that effectively nobody makes progress. So we have full starvation of all of the threads that are waiting for associated resources. The result is effectively that we have lots of threads, but unfortunately, zero progress. So let's look at some examples. On the left here, we have thread 1 that's locking the red lock, then the blue lock, then doing some processing, then unlocking the blue, then unlocking the red. Notice I kind of drew the dotted lines on the left. It shows that these nest. It's not required that your locks always nest, and actually if you think about hand-over-hand locking that we've talked about multiple times, the locks do not nest in this way. But you'd often think that sometimes you'll call into some sort of a function that's there to maintain the abstraction for a resource, let's say a linked list. So you could imagine you'd take a lock at the start of a function and release it at the end. And if you invoke another function that uses another resource, then you'd imagine there's a lock at the beginning and the end of that too. So here we see kind of a sequential flow of code, but you might imagine that's spread up across multiple functions, which, naturally are going to have a lot of nesting. But what I want to point your attention to here is that thread 2 on the right is in a situation where it's locking the blue lock first, then the red lock, right? So we have this interesting situation where the locks are being taken in different orders. And if we look at what that actually does, the red lock is taken by that thread 1, the blue lock is taken by thread 2, and immediately, when thread 1 tries to take the blue lock, it cannot. Of course, the critical section is held by thread 2. However, when thread 2 tries to take the red lock, we have a similar situation. It notices that that critical section is taken by S1, so therefore it needs to block. So we have each thread blocked, waiting for a lock that the other thread owns, while holding the lock being blocked on by the other thread. This is effectively what we call deadlock. And let me give another example that we've talked about multiple times in the class. So imagine that you have a linked list, and let's imagine that you want O of 1 removal from that linked list, so you use a doubly linked list. This is an exceedingly common technique, and because a data structure, let's say like a process for instance, or in the memcache example that we talked about before, just a key value pair. It might be in multiple lists. We might have the chain list for the hash table, and we might have an LRU list that it's on. In an operating system, we might have a list of all of the processes within the system, and then we might have a wait queue, a run queue, all of those lists that we talked about before. So if you want to kill a process, you're going to need to remove it from all of those lists. So you can imagine that we want O of 1 removal to avoid all of the overhead there, right? O of 1 removal means that you typically want doubly linked lists. So you might have a situation like this, where a thread on the left wants to delete delete its node, in this case the one holding the the one with the left blue lock. So if we want to remove it, then we're going to need to remove it from linked list. We want to take all of the locks, including the lock for the next and previous node, because we need to change their pointers, fix up their pointers, their next and previous pointers. So what do? Okay. First we take the blue lock, of course, that's our node. Then we take the red lock for the previous node. Then we take the red lock for the next node. Okay, so that's what we want to do, right? But as of now, we just have taken our first lock. A thread on the right actually wants to remove the node on the right, which is the right red lock, right? So it takes the red lock for that node. And you can see they're adjacent within the linked list, so you might already get an intuition about where the problem is here, right? Next, it's going to lock the blue previous lock and then the blue next lock, right? And of course, what we see is that the left thread, it goes through, takes all of its locks, but when it tries to take its next red lock, it'll block because it cannot, the thread on the right has already taken that lock. And unfortunately, the thread on the right will get to execute at that point, but the first thing that it will do is, I have a error here. It'll try to take the blue lock. You can see it's trying to take the red lock there. Yeah, that arrow is supposed to be pointing to the blue lock. So now we have both of the threads holding a lock for their current node and trying to take the lock for the next or previous node respectively, and blocking because they cannot take it. We have deadlock. Both of the threads are waiting for a resource held by the other thread. This is effectively what we think of when we think of deadlock. So you can see it's a little tough. It means that now we don't just need to worry about race conditions, we don't just need to worry about fine-grained locking, but we also need to worry about deadlock, which is a consequence often of fine-grained locking, but can happen because of things as innocuous as malloc as well, right? So the big observation here is that the order of lock acquisition really, really matters, right? So what we're going to talk about in this lecture is essentially how we can understand what orders are dangerous and how we can either prevent by design at design time or avoid using dynamic checks this notion of deadlocks, okay? So first let's try to define it, and let's try to understand how the ordering matters and what defines a dangerous order. First, I'm actually going to go through an example, yet another example. This is intuitive, this is high level. Imagine that we have 4 intersections as such, and we have traffic going corresponding to the arrows, right? And where you have an arrow, you can imagine there's a convoy of traffic, of cars, just heading down that lane, right? So if we have a situation that looks like this, then the traffic going from the right to the left in the top lane has been given access to the intersection top right and the top left and is flowing through that intersection, right? And we all know that, of course, what happens when that's done in traffic? Well, you have a green light for that traffic, and you have a red light for the other traffic going in the orthogonal direction, right? So the traffic coming from the top left has to stop at a red, right? So we can actually think of intersections as contended resources and them being allocated to the different threads, right? And if you kind of follow through the logic here, we might think that there's a situation where each of the flows of traffic is given access to one of its intersections but not the other, and it might look something like this. And now we can see that that can actually end up in a place where you've all been allocated one of the resources and are trying to take another, but that's taken by another flow of traffic, in this case, by another thread that has a resource and is trying to take another, right? So this is deadlock, and it happens. Never fun, of course. But the nice thing about this in traffic is that though it's obviously going to slow the traffic down a huge amount, humans are pretty adaptive, right? Computers are not, right? You need to explicitly add the code to deal with these types of situations, whereas humans, they're going to find a nook and cranny that they can squirm through and eventually resolve the deadlock, right? Okay, so let's really define what's happening in the system here. We're going to define a model of the system that really captures kind of the salient points that we care about to define deadlock. So let's imagine that we have three different resources, or a number of different resources, R1, R2, R3. These might be CPUs that we're allocating to processing. They might be devices that we're allocating to a process, malloc that we're mallocing, or data structures protected by critical sections, right? And each of these resource types, RI, has WI instances that can be allocated. For a critical section, there's only one instance, right? But for memory, you can imagine the instances are essentially the number of bytes or pages or something, some unit of memory that you have within your process, right? It might be a counting semaphore. We didn't talk about this in terms of the abstractions for synchronization. A counting semaphore is just a mutex that can have n items and threads within a critical section, right? I'm not going to go into why it's useful. It's somewhat undermotivated. And all of these processes we're going to think of as having a access pattern that looks like this. You can request access to the resource, then you use it, and then you release it. Request might be malloc, where release is free. Request might be lock, where release is unlocked, depending on the type of resource. Okay. Now, if we think about this as the model, then what we can say is that deadlock can arise if four conditions hold simultaneously. Now, can is a very important word here, right? It's saying something similar to how we talked about race conditions previously. Race conditions can happen if we don't synchronize around the proper shared memory within our system, but they aren't guaranteed to. It's a probabilistic argument. Same thing here, right? Deadlocks can arise if four conditions hold simultaneously. So the first one is mutual exclusion. If the resources can only be held by essentially one process at a time, fine. We've talked about mutual exclusion many times. Hold and wait. This is essentially where a process holds a resource and can wait to get another. So that's if we take two locks, right? We hold a lock, we want to take another lock. If we call malloc and we call malloc again. If we call malloc and then we take a lock, right? All of these are instances of holding some resource and then potentially waiting for another, right? Additionally, no preemption is important. This is essentially saying that a resource can be released only voluntarily by the process holding it after they're done using it. So this goes back to what we talked about. You have to request the resource, use it, and then release it. You cannot have the resource yanked from your possession before you release it. You must voluntarily release it, right? You can imagine that implies that there is preemption in some systems, and effectively this is a lot of the technology that underlies some database implementation. And importantly, we have circular wait, right? So not only do you need hold and wait where you hold some resource and wait for another, but there needs to be some sort of a cycle within those relationships. So we can think of there being a number of processes that are all asking for resources, P0 through Pn, and you can imagine they're all waiting for some resource, and that resource is held by some other process, right? And the P0 is waiting for a resource held by P1. P1 is waiting for a resource held by P2, so on and so forth. And if we go to the very end, Pn is waiting for a resource held by P0. That makes it circular, right? So this is simply the idea that you have this set of processes, all of the waiting is configured in this way where it becomes cyclical, right? So let's just look at these using examples. Mutual exclusion, we know what that is. If there are locks, there's mutual exclusion, fine. Hold and wait, we hold a resource, we hold a lock, and we're potentially waiting for a second one. Great, we saw the example with that last time. And we have circular wait. And we saw what this looks like, where we can be waiting for the first lock, and then we can get the first lock and then wait for the second, whereas thread 2 gets the second lock and then waits for the first. And you'll notice, what's the probability that we're going to get preempted between either of the two lock calls for each of these threads, and then switch to the other thread exactly when it wants to take the lock? The probability is relatively small in many cases, right? So this is actually what makes deadlock so pernicious and so difficult, that like race conditions, it doesn't manifest commonly, so it becomes exceedingly difficult to debug. So what that means is that you need to know it exists, and you need to design your system in a way that it just won't happen, right? You need to try to design it out of your system because it's nearly impossible to actually test, right? Okay, so when can we have deadlock? Let's imagine the system between these processes and resources is a graph. And we're going to call each of the vertices either a process or a resource, okay? Each of the edges is essentially one of two types. Either a request edge, when a process is trying to, for instance, take a lock or malloc memory, and it requests some of that resource. At that point, the system might realize that that lock is already taken by another process, therefore it cannot take it right now. Or we try to allocate memory and there's no memory available, right? But regardless, we're just requesting some resource. However, when we return from that request, when the lock returns, when the malloc returns, we have been assigned actual resources. So now we have an arrow from one of the resources, one of the WI resources within the resource type that goes to that specific process. So it's been allocated effectively. Visually, we're going to show this as a process being circular and our resources being a box. And if it's a resource with multiple instances, then it looks something like this. We have 4 instances within that resource type. So when a process requests an instance of the resource, we point to the resource type. This is, again, we're waiting for a semaphore that's trying to take a semaphore. Again, a semaphore is basically a mutex that can be taken, that can have multiple threads in the critical section. In this case, 4 threads within the critical section. Or we might be calling malloc, right? When PI is assigned a specific instance of the resource, we take that instance and add a pointer back to PI, right? Okay, so what does this end up looking like if we take what we talked about as an example previously and reflect it into this model? Well, if we look at this resource allocation, we can reflect it into a resource allocation graph as such. So we can see that this flow of traffic on the left from the top is allocated the top intersection. So we have the top intersection on the right in the model as an arrow pointing to the process because it has been allocated to it. That process, however, is requesting the bottom left intersection, the bottom left resource, which has been allocated actually to the process for the traffic flow coming from the left. And you can see that if we view the system as this weights for graph, then what we end up having is a visual cycle within this graph, right? So let's look at some additional examples of this. Penny absolutely adores these problems, right? Basically because they're her balls, so that she can chase them and shoot them. Squeaky toys. That's all she cares about in life. Doesn't care about food. Squeaky toys are her jam. I'm amazed that you constantly don't hear her squeaking stuff in the background. Now you're just hearing her claw the ground because she's playing with a bug, you know. So, whatever. This resource allocation graph, we have process 0 requesting a resource for the top left resource. We have process 1 that has been allocated one of the top left resources and one of the bottom resources as well, right? And is requesting a resource on the top right, which is owned by P2. So the question here is there deadlock, right? Now, remember when I talked about the conditions, I said you can have deadlock. So just because all of the conditions might be true doesn't mean that you actually have deadlock, right? So just think through this example. Do you think that there's actually deadlock? I'll give you a second. There's actually not deadlock here, right? Because what's happening here is that you do have a kind of these interesting resource allocations where, you know, this bottom resource is partitioned out to P0 and P1, and you start to have what looks like a cycle going from P1 through the top resource to from P0 through the top resource to P1. But as of now, we don't even actually have a cycle. And if P2 released its resource and P1 got that, it might release its bottom resource, might release its top resource, which would let P0. You know, there are a lot of dynamic resource allocation decisions that could be made from this point that will mean that the system is absolutely not in deadlock, right? So it's not in deadlock now. It might not continue into deadlock. Penny, very, very excited. Basically showed her a squeaky toy here. She loves this, right? Chasing the balls. Okay, is there deadlock? All that I've done is add a arrow going from P2 where it is requesting a resource on the bottom here. Is there deadlock? Pause. Ask yourself, is there deadlock? There is deadlock here, right? So we have P0 waiting on this resource that is owned by P1, P1 waiting on this resource that's owned by P2, P2 waiting on a resource that's owned by P0 and P1. And they're both actively waiting for resources that, in effect, are creating a circular wait between all of these different processes, right? So we have the cycle, we have hold and wait, we have a lack of preemption, we essentially have deadlock in this situation, right? Okay, how about this case? Penny isn't as excited about this one, and she just decided that she's getting so much attention right now from all of you that she's just going to look adorable. So, you know, this is basically her, oh, look at me, I'm adorable, you want to give me pets? Type of look. But we have work to do. Sorry, Penny, not now. We got to be serious. Deadlock. All right, is there deadlock in this case? Pause it, figure it out, come back. There's actually not deadlock. And this is weird, right? Because we have circular wait between P0 and P1 effectively, right? So intuition would say, oh, well, P0 holds a lock and is taking a lock. P1 holds a lock and is taking the same lock that P0 holds. We must have circular wait here. But the bottom resource is not a lock. It has multiple resources, and P2 is kind of the key here, because P2, if P2 were to go wait on, the top resource, yeah, okay, we have deadlock. But we don't know that it's going to do that, right? Right now we do not have deadlock, because P2 might also just release its bottom resource, allowing P1 to take it, which might allow P1 to release its top resource, which might allow P0 to take it, etc., right? So we do not have deadlock yet. So when you have multi-instance resources, circular wait is not sufficient for being able to suss out whether you have deadlock right now, right? Okay, so if the graph contains no cycles, there's no deadlock. It's simple as that. If the graph does contain a cycle and you have one instance per resource type, you have deadlock. That's it. Game over, right? Lack of progress for those resources and those processes forevermore. However, if you do have several instances per resource type, then deadlock is possible, but not certain. In no way certain, right? Okay. How can we deal with this, right? Deadlock seems bad, and it is. When I was growing up, I used, Windows 95 a lot, right? And some of the preceding versions. And it was really bad, like 95, 98, ME, all of these things, like it would just kind of lock up every once in a while. And if you've ever had your system lock up, it happened a lot, we'll say back then, right? And what was happening oftentimes was effectively that we had deadlock. And you just had these systems that were engineered in such a way that they didn't really try to systematically prevent deadlock. And you couldn't really test the system because it was so complicated and deadlock is so nuanced, as we've kind of been learning, that it was really hard for them to find all of these cases where you'd actually have deadlock. So there was a kind of very long time when your system would just lock up and you would reboot, right? Still actually happens for me on Linux, unfortunately, with a somewhat regular frequency, but that's more so probably because of graphics card glitches than anything else. So what do we do about it, right? Let's talk about kind of the strategies. So there's one class of strategies that essentially say we never want to enter into a deadlock. And there are two classes of strategies for trying to approach that. One is by design, preventing deadlocks from ever happening within the system. This is pretty common. The other is by avoidance, using dynamic algorithms to try to detect if we allow a resource to be assigned to a process, is it possible that deadlock could happen? If it's possible, then don't make that resource allocation right now. The second class is to essentially basically allow the system to execute, allow deadlocks to happen. Obviously, you want to try to prevent them, but if your code has a bug and you have a deadlock, then figure out how to detect and recover from those deadlocks, right? And unfortunately, most actual practical systems, they try to prevent it by design, but in a kind of ad hoc way. It's not like formally proven or anything. So you kind of just use the ignorance, luck, and cross fingers to try to hope that the system doesn't have deadlock. Unfortunately, this is all too common. Okay, so if we want to, at design time, prevent deadlock from ever happening, we basically have to go back to the four conditions that we talked about before and try to essentially make it so that one of those conditions never happens, right? So mutual exclusion, we can't really compromise here if we're allowing something to have a resource. Well, fundamentally, some resources need mutual exclusion, right? Critical sections, memory, all of these things. So you can't really get away from mutual exclusion in a lot of cases. Hold and wait, there's a lot that you can do here, right? So you essentially want to guarantee that when a process is going to start accessing resources, it effectively gets access to all of the resources at once or waits for all of them at once. This is a fancy way of saying use really coarse-grained locks, right? If you use coarse-grained locks that protect all of the data structures that you're going to access, then fantastic. You're never going to have deadlock because you never hold that lock and need to wait for another. You only have that one lock. But the downside here is that you have very, very low resource utilization because you don't have fine-grained locks, right? You aren't going to have parallelism, and all resources have to be assigned at once. Note that this also applies to memory. So you need to be allocated all memory at the time that you essentially want to do anything for any of the requests you could potentially make, right? So this is why low resource utilization kind of plagues this type of system. You most likely are not going to request all of the memory that you kind of need to provision for, but you need to provision for it if you're going to use this type of approach. So this is used in the context of coarse-grained locks, but only in a case where you can give up on parallelism and all of that. Okay. Preemption is kind of a hard requirement as well, but there are systems that are actually designed around the idea that if a process holds a resource and makes a request for another that can't be satisfied, then we just go back and release all of the resources that we had before, and then essentially block waiting until we can try to take them all again. And try locks are essentially a mechanism that could be used to do this. We didn't go into the API for this, but it's a simple idea. Instead of just having lock and unlock for our locks, we could have a try lock call. And many of you have already seen this because you were looking at the man pages in pthreads and you saw this try lock feature. And the essence of try lock is that you try to take a lock, and if you can take it because it's not contended, because it's not owned by somebody else and somebody else is not in the critical section, then you take it. However, if somebody is in the critical section, then instead of blocking, the try-lock returns with an error code saying that you couldn't go into the critical section. So you can use try-locks to effectively try to take all of the locks that you might need, and then to go through the computation of your process, taking the locks one by one. But once you cannot take one of the locks, then you have to go back, release all of the locks that you have, and then try again. So we're essentially kind of preempting ourselves out of the critical section and retrying again. This is again a idea that's fairly pervasive in data structures. It's not implemented in this specific way, but optimistic concurrency, which you can Google for, is one technique for essentially doing this. Circular wait is also something that you can actually prevent. And this is exceedingly common. This is the most common way for us to try to prevent deadlocks flat out. And we essentially try to impose a total ordering on resource acquisition. So from a lock perspective, that means that we always take locks in the same order, okay? So we always take them in the same order, which means we're effectively imposing a total order in which ones we take before which others, right? This is in a pervasively used technique where we essentially say, well, okay, if doubly linked lists are kind of a huge issue and can cause deadlock, what's the core of that? Well, it's effectively that we're not always taking locks in the same order. Sometimes we take the lock and then the next lock. Sometimes we take a lock and then a previous lock. And because of this fact that we can sometimes take lock A, then lock B, and then sometimes lock B and then lock A, we are not imposing an ordering on those lock-taking operations. So this is where we essentially said, no, you can't do that. Instead, you have to use something like hand-over-hand locking to iterate through the linked list to find the node that you're looking for instead. Hand-over-hand locking is a kind of mechanism that intuitively enforces a total ordering on the lock ordering within that linked list. The other broad approach that we can take is avoidance, right? And this is dynamic. This is when resources are requested, we can decide whether to actually allocate them to the resource or not, because we can essentially try to ascertain if we give them access to this resource, if we allow them to take this lock right now, in the future, can that cause a deadlock, right? We aren't trying to say, is deadlock happening right now if we if we assign this resource necessarily, where we could also be looking forward into the system. So what we do is I dynamically observe the pattern of resource allocation given the system state and decide if it's safe to allocate the resources. So we need to track all of the taken resources and make a decision based on a request whether we should allocate it. Typically, this is done by requiring all processes to declare the maximum number of resources, all of the resources that they need of each type a priori. So we need to know every single resource that they might take during their execution. And the deadlock avoidance algorithm will observe the current allocations made to each of the processes and essentially say, if I allocate this resource to you, is it potentially possible that you will go on and take another resource that would cause deadlock, right? Or could you request a resource that's taken by another thread that could result in circular wait? That potential allocation is what we're trying to prevent. Let's kind of think about what that might look like. So if we have a system where all of the resource types are single instance resources, as the intersection example that we've used before, and we have traffic coming from the top right, and we have essentially a traffic light, you can think of it like a lock, trying to decide whether we should actually allocate that intersection to that flow of traffic, it will need to actually think through what could happen if we allocated that resource. And the algorithm would essentially need to realize that could lead into the situation where then that flow of traffic would request the top left intersection resource, which would result in deadlock. And because of that potential future allocation, it would essentially need to prevent this current allocation. There is an algorithm for doing this for multi-instance resource types, Dyker's algorithm. I used to actually teach this, but I just don't actually think it's pragmatically that useful or interesting nowadays. So I encourage you to look it up on Wikipedia, but I'm not going to go into it now. Okay, now we get into detection and recovery. These are actually pretty quick. So detection, I think, is actually pretty intuitive. We just need to have like a background kernel thread or something that wakes up periodically and looks at all of the resource allocations in the system and determines if there's deadlock. What is the algorithm for doing that? Well, we would essentially need to look at the resource allocation graph and decide whether there's a cycle. This is a pretty practical approach because it doesn't need to, like the avoidance algorithms, it doesn't need to have this notion of what is the maximum number of resources of every type that it can use to make these future predictions about resource allocation. Instead, it just looks at the current allocations, right? So it's pretty practical. And you can imagine that we take a resource allocation graph and we would compute what's called a weights for graph. And this is effectively trying to ask for every process, what is the corresponding process that holds the resources that this process waits for. And if we generate this weights for graph between processes, all that we need to do is effectively determine whether it has a cycle. And it's kind of a famous interview process. An interview question when you have a linked list or something like it to determine whether there's a cycle in it. So I encourage you to figure out the algorithm for computing that for no other reason than because it is something that's asked on interviews. But you could apply the same type of logic here to determine whether there's actual deadlock in the system. And if there's deadlock, the question is, what the heck do you do, right? So there aren't many good options here, and effectively you kind of need to add preemption into the system, and preemption in this case is termination. So the processes that are involved in those resource acquisitions, you essentially need to figure out a way to terminate them. And this is, if the deadlock's in the kernel, then that's not really possible because you're talking about kernel resources that are being taken. So often deadlock in the kernel results in rebooting your system. But if you notice that processes, for instance, are stuck in some sort of a cycle, as we saw before, then you can abort all of the deadlocked processes, or you could just kill them one at a time, allowing potentially them to resolve their deadlock because one of the processes is removed from the cycle, right? But you have all these difficult questions. Which process do you kill? In which order do you kill them? And a very practical instance of this that probably most of you have actually seen working in your system is the out-of-memory killer in Linux. And this is effectively the thing that kicks in when you are out of memory and you have no memory. All of the processes are probably stuck, blocked, waiting for memory allocations. They're all trying to do malloc, but none of those malloc calls can be satisfied because all of the instances of the memory resource have been allocated out to the processes. So what do? Again, you recover from the deadlock by effectively trying to shoot down, kill those processes. But the question is, which ones do you choose? And this is a notoriously difficult heuristic-based algorithm, and some of the early versions incurred the horrible wrath of Linus because it would kill things like the X Windows server that would just take down all of your graphics, which has the effect of making it seem like your system needs to reboot, so not that useful. So writing a generic algorithm that will figure out what to actually kill, what processes to release, is really, really hard. The naive thing of, well, we're out of memory, kill the process that's using the most memory, is not necessarily what you want, because that might also be one of the most important processes on your system, right? So this is the heuristic base. There's no good way to do this, but they've happened on a few ways that seem to work out okay on desktops at least. On servers, yeah, you just need to design your system so that you don't run into this type of situation. So deadlock is a really pernicious problem. It is something that is hard to test, hard to debug, because it is a probabilistic activity, or like race conditions, right? We don't know if it's going to happen. We just know that it can happen in some cases, right? We observed what those cases are, right? And it just comes down to the dangers of dynamic resource allocation. If you can statically allocate all of your resources, then you're essentially getting rid of hold and wait, and you have a system that works essentially without any problems. But you're statically allocating all resources, so you have a problem, right? You don't have as good of resource utilization. So it's really a consequence of dynamic resource allocation. And asking for critical sections for locks is resource allocation, right? We're allocating a critical section to a given thread. So what this means for locking is that we have to be really, really careful about the ordering of how we take our locks. And you pretty much want to define for every data structure and for every flow of control how you take those locks. What this practically means is within a data structure, if you're using any amount of fine-grained locking, define the lock ordering within that structure. If you have different data structures that might be accessed with kind of nested locking, then you had better define the order in which you access those data structures. You cannot take them out of order, right? This does complicate even simple structures like linked lists, as we saw doubly linked lists, because it means that the doubly part of that effectively can't really exist if we're going to use a defined lock ordering. But I also want to say, we think about these deadlocks as applying to locks most frequently, but it really applies to general resources. And we saw an instance where it applies, for instance, to memory, right? And that is a big problem, because the out-of-memory killer is a consequence of deadlock, and it does bad things to the system, but recovery is a necessary evil. So, hopefully this has given you a good amount of context about deadlocks and how we think about solving them. Hopefully you've gone over enough practical examples that you feel like you could apply it. This is the type of thing that you just need to think carefully about and design your system well. All right, operating systems people, thank you very much. Hope you enjoyed this, and tune in soon. Bye.